Somewhere beneath the streets of Los Angeles, in rock that has not moved in over 300 years, the pressure is still building. Nobody can see it. Nobody can hear it. But scientists say it is there, coiling tighter with every passing month. And for the first time, a new model has put a number on exactly how bad it could get. It is not a rumor. It is not a viral prediction from social media. It is a study built on 1,000 years of earthquake history. And what it found has confirmed the one fear California has been trying not to think about for decades. The San Andreas Fault does not run in a straight line. It bends, it splits, it tangles with other fault systems in ways that scientists are only now beginning to fully map. And at one particular point northeast of Los Angeles, a narrow corridor of crushed rock known as Cajun Pass, researchers have discovered something that changes the entire calculus of California's earthquake risk. This is not just another fault. It is a gate. A place where an earthquake starting on one fault system can leap onto another, turning what should have been a contained, survivable event into something far larger and far more destructive. For years, seismologists have treated the San Andreas and the San Jacinto Fault as two separate threats, each capable of producing a serious earthquake on its own. The San Andreas is the longer, more famous of the two, the fault that ruptured in 1906 and devastated San Francisco. The San Jacinto runs closer to San Bernardino and Riverside, slicing through some of the fastest-growing suburbs in Southern California. Millions of people live directly on top of both. But new research examining roughly 1,000 years of seismic history has found something that keeps geologists awake at night. These two faults are not independent. They are connected, and Cajun Pass is the connective tissue between them. Using data pulled from trenches dug directly across the fault lines, from layers of soil and rock that record centuries of ancient ruptures like rings inside a tree, scientists reconstructed a timeline of ground-shaking events stretching back a millennium. What they found was a pattern of shared stress. When one fault builds pressure, the other feels it. When one slips, the other becomes more likely to follow. The two systems, researchers now believe, are simultaneously carrying dangerously high levels of built-up strain, and Cajun Pass sits precisely at the point where a rupture could jump from one to the other. To understand how researchers even arrived at the Cajun Pass discovery, it helps to understand how paleoseismology actually works, because the process itself is almost as remarkable as what it uncovered. Scientists dig narrow trenches directly across a fault line, sometimes 20 or 30 feet deep, exposing layers of sediment that have been quietly accumulating for centuries. Each time the fault ruptures, it offsets these layers, snapping them sideways or vertically in a way that leaves a permanent scar in the geological record. By carefully dating the organic material trapped within each layer, using techniques like radiocarbon dating, researchers can reconstruct not just how many earthquakes have struck a given stretch of fault, but roughly when each one occurred, sometimes with a precision of decades rather than centuries. It is slow, painstaking work, the kind of science that unfolds over years rather than headlines, and it is precisely this kind of patient reconstruction that revealed the shared stress pattern between the San Andreas and San Jacinto systems. What makes the Cajun Pass corridor so significant is its geometry. Fault systems do not simply end in a clean line the way a crack in a sidewalk might. They fray, overlap, and in some places run close enough to each other that the stress field generated by one system directly influences the rock surrounding the other. Scientists refer to these connection points as earthquake gates, structural features that determine whether a rupture starting on one fault dies out naturally or finds a pathway to keep traveling onto a neighboring system. Cajun Pass, sitting almost precisely between the San Andreas and San Jacinto faults, functions as exactly this kind of gate, and the geometry there, according to researchers, appears more open than previously assumed, more capable of allowing a rupture to pass through rather than stopping it. This is not a purely theoretical concern rooted only in ancient trench data. Modern GPS monitoring stations scattered across Southern California continuously measure the almost imperceptible creep of the ground, tracking how much strain is accumulating along different fault segments in real time. When researchers cross-referenced this modern strain data with the historical rupture patterns pulled from the trenches, they found that both the San Andreas and San Jacinto segments feeding into Cajun Pass currently show unusually high, simultaneous stress loading, a combination that, according to the study's authors, has not been observed together in this way before in the available scientific record. It does not tell them when. It tells them that the ingredients for a larger connected rupture are, for the first time in documented history, all present at once. Here is why that detail matters more than almost anything else in California seismology right now. A single fault rupture is dangerous enough. But if the ground breaks free on both the San Andreas and San Jacinto systems in one connected event, the result is not simply a bigger version of a familiar disaster. It is a fundamentally different kind of earthquake, one capable of releasing far more energy over a far longer stretch of time. sending shockwaves through cities that were built block by block without ever fully preparing for the possibility that these two faults might break together. To understand why researchers are calling this scenario one of California's worst fears, you have to go back to the fault's origin, deep in the geology of the American West. The San Andreas is not a single crack in the earth. It is the boundary between two enormous tectonic plates, the Pacific Plate and the North American Plate, grinding past each other in agonizingly slow motion at roughly the speed a fingernail grows. That may sound harmless. It is not. Over millions of years, this slow grinding has sliced California's crust into a labyrinth of interlocking faults, more than 300 of them mapped across the state, some capable of triggering the others in a domino effect that scientists are still working to fully understand. The fault has ruptured catastrophically before. In 1906, it tore open along roughly 290 miles of Northern California, flattening San Francisco and killing thousands in the fires that followed. In 1857, a rupture along the southern segment near Fort Tejon sent a wave of destruction through a sparsely populated region that, today, would sit directly beneath millions of homes, freeways, and office towers. Since then, the fault has been unusually, almost eerily quiet along its southern stretch. And in earthquake science, quiet is not comforting. Quiet means the strain is still accumulating, still waiting for a release. This is the backdrop against which the new Cajun Pass findings landed like a thunderclap inside the seismology community. Because if the fault's long southern silence has simply been decades of pressure building without relief, and if that pressure is now shared between two connected fault systems rather than contained within one, then the eventual rupture may not look like anything California has planned for. It may not be the tidy, single-fault scenario etched into decades of emergency planning documents. It may be something bigger, messier, and far harder to contain. It is worth pausing here to appreciate just how much California's relationship with earthquake risk has evolved since the state first began seriously studying it. In the years following the 1906 San Francisco earthquake, scientific understanding of faults was rudimentary at best, built largely on observation of surface damage rather than any real insight into the deep tectonic mechanics driving the destruction. It took decades of advancement in seismometer technology, in plate tectonics theory, in computing power, before scientists could even begin to model how these systems behaved beneath the surface. The first uniform California earthquake rupture forecast, released years ago, represented a genuine milestone, an attempt to build a statistically rigorous, statewide picture of earthquake probability. Its successor, the third version of that same forecast, added 150 additional mapped faults that scientists in the earlier era simply did not have the data to include. Faults whose potential to cause damage had gone almost entirely unaccounted for in official risk models, until GPS monitoring finally revealed how much strain was quietly building along them. Every revision of this forecast has told essentially the same underlying story, refined with sharper and sharper detail. California's crust is not a handful of isolated cracks. It is an interconnected web, closer to a braided river system than a simple line on a map, where dozens, sometimes hundreds, of individual fault segments interact in ways that remain only partially understood even today. The Cajun Pass findings represent the latest chapter in that same ongoing story, a chapter that narrows the uncertainty just enough to make the danger feel, for the first time, genuinely tangible, rather than statistical. And the warnings did not stop there. Just weeks before the Cajun Pass findings became public, a devastating magnitude of 7. 4 earthquake tore through western Colombia, killing hundreds and leaving thousands more displaced. It came almost exactly as one independent forecaster, geophysicist Stephen Burns, had warned it might after he had flagged unusual seismic activity across the Caribbean plate months earlier. Burns has no formal peer-reviewed model behind his forecasts, and mainstream seismologists are quick to note that earthquake prediction, in the strict sense of naming a date, location, and magnitude in advance, remains scientifically impossible. But his track record on Colombia was enough to make people listen when he turned his attention to California and delivered 4 words that spread across the internet within hours. California is super overdue. Burns' theory rests on the idea that seismic energy released by a massive earthquake does not simply vanish at the epicenter. It radiates outward through the Earth's crust, transferring stress to fault systems thousands of miles away, occasionally nudging an already strained fault past its breaking point. He points to a pattern. A magnitude 7 earthquake in Venezuela in 1997 followed 2 months later by a major quake in Colombia. And now, in the current year, 2 large Venezuela earthquakes preceding the deadly Colombia rupture by roughly 6 weeks. If the pattern holds, Burns argues, the American West Coast may now be sitting inside a dangerous window, with Southern California facing elevated risk over the next 6 to 12 months. Established seismologists are careful to separate this kind of pattern-based warning from confirmed science. The United States Geological Survey has stated plainly, more than once, that neither it nor any other scientific body can currently predict the precise timing of a major earthquake. What they can do is calculate long-term probabilities, and those probabilities, on their own, are frightening enough without any need for exaggeration. This is where the real, peer-reviewed research takes over the story, and where the fear stops being speculative and starts being measured. Caltech seismologist Dr. Lucy Jones has spent years developing what has become the most detailed simulation of a major San Andreas rupture ever built, a scenario researchers refer to simply as the big one. Her model imagines a magnitude 7, an earthquake tearing along the southern San Andreas fault, and the numbers it produces are almost impossible to fully absorb. Nearly 2 full minutes of violent, continuous shaking. Not the sharp jolt most people picture when they think of an earthquake, but 2 minutes of the ground itself refusing to hold still, long enough for buildings to fail in slow motion, long enough for the human brain to move from shock into pure animal panic and back again before the shaking finally stops. The fault line crosses beneath critical infrastructure that the entire region depends on to survive, including the aqueducts and pipelines that carry water from hundreds of miles away into a desert city of millions. In Dr. Jones's scenario, these systems do not merely get damaged. They get severed, cut cleanly where they cross the rupture zone at a moment when the region needs water more urgently than at almost any other point in its history, for firefighting, for hospitals, for simple survival in the days after the ground stops moving. The San Andreas, researchers note, is the longest fault in the state, which means it is capable of producing the largest earthquakes California can generate. Length translates directly into energy, and energy translates directly into destruction. Zoom out from Southern California, and the picture only becomes more unsettling. The United States Geological Survey's most recent national hazard model estimates that roughly 159 million Americans currently live in areas exposed to strong or very strong earthquake shaking risk. That is not a Southern California statistic. That is not even a California statistic. That is nearly half the population of the entire United States, living, working, and raising families across a landscape laced with fault lines that most people never think about until the ground beneath them starts to move. The human stakes of this discovery come into sharper focus when you consider who, exactly, lives along this stretch of geography. San Bernardino and Riverside counties, sitting almost directly atop the San Jacinto Fault, and within striking distance of Cajun Pass itself, have experienced some of the fastest population growth of any region in California over the past 2 decades, driven largely by residents priced out of coastal cities, searching for more affordable housing further inland. Entire new subdivisions, logistics, warehouses, and transportation corridors have been built across this landscape in just the last generation, often with limited public awareness of exactly which fault segments run beneath them. Cajun Pass itself is not simply a geological curiosity. It is also a critical transportation choke point, carrying interstate highways, rail lines, and fiber optic infrastructure, connecting Southern California to the rest of the country. A rupture at precisely this location would not only unleash a larger earthquake, it would sever some of the most vital transportation and communication arteries the region depends on at the exact moment those arteries would be needed most. Emergency planners have spent years running earthquake drills built around scenarios like the Great California Shakeout, the largest earthquake preparedness exercise in the country, training millions of residents to drop, cover, and hold on in anticipation of a major single-fault event. Those drills remain valuable, scientists are quick to note, because the basic physics of surviving violent ground shaking does not change whether the rupture involves one fault or two, but the broader response planning, the assumptions built into hospital surge capacity, emergency water distribution, and transportation rerouting has historically been calibrated around scenarios smaller in geographic scope than what the Cajun Pass connection now suggests may be possible. Updating those assumptions is not simple. It requires remodeling infrastructure vulnerabilities, retraining emergency personnel, and, in many cases, securing funding for retrofits that had previously been deprioritized because the underlying risk was assumed to be smaller than researchers now believe it to be. There is also a deeper, more unsettling layer to the Cajun Pass story once you consider how it interacts with the rest of California's fault network. The San Jacinto Fault does not exist in isolation any more than the San Andreas does. To its south, it runs close enough to other active fault systems near the Salton Sea that some researchers have long wondered whether a large enough rupture could theoretically cascade even further than the San Andreas connection alone suggests. This remains a subject of active scientific debate rather than settled fact, and researchers are careful not to overstate a connection that has not yet been rigorously confirmed. But the very existence of that open question illustrates just how much remains unknown about the full extent of California's interconnected fault network, even after more than a century of dedicated study. And the threat is not confined to the faults everyone already knows about. Researchers studying tiny, almost imperceptible earthquakes beneath Northern California, tremors thousands of times too weak for a human being to ever feel, have uncovered something scientists did not expect. Using a dense network of seismometers across the Pacific Northwest, tracking how these microscopic quakes respond to the same tidal forces that pull the ocean's tides in and out, a research team found that the underground structure beneath the region is far more complicated than the standard three-plate model has always assumed. There are, in fact, 5 moving pieces beneath the surface there, not 3, with 2 of them hidden entirely from view until this new tidal tracking method exposed them. This matters because 2 of the West Coast's most dangerous fault systems, the San Andreas in the south and the Cascadia subduction zone stretching from Northern California up through the Pacific Northwest, may be more directly connected than scientists have ever previously confirmed. If that connection is real, then a major rupture in one system does not stay neatly contained within its own geographic footprint. It has the potential to influence, or even trigger, seismic activity in the other, turning California's earthquake risk into something closer to a chain of interlocking dominoes stretching along nearly the entire length of the West Coast. None of this uncertainty is unique to California, and it is worth remembering that the state's earthquake risk sits within a much larger national picture that most Americans rarely think about. Far from the West Coast, the New Madrid fault zone beneath Missouri and Arkansas has produced some of the most powerful earthquakes in recorded American history. Sequences from the early 19th century so violent they reportedly rang church bells as far away as Boston. That fault has been comparatively quiet for generations, and scientists studying it face precisely the same core dilemma seismologists face in California: an inability to say with certainty when accumulated strain along a historically active fault will finally release. Overseas, researchers monitoring the Campi Flegrei volcanic caldera near Naples, Italy, have spent years tracking accelerating ground uplift and rising seismic activity in one of the most densely populated volcanic regions on the planet. A slow-motion warning playing out in real time for the millions of people living within its shadow. Faced with a threat this complex, scientists have spent years working on a different kind of breakthrough. Not a way to predict earthquakes, which remains firmly outside the reach of current science, but a way to prepare for them faster and more precisely than ever before. Earlier this year, researchers unveiled a new computational approach capable of running complex seismic simulations roughly 1,000 times faster than previous methods allowed. It will not tell anyone when the next major quake will strike, but it means cities, emergency planners, and infrastructure engineers can now model dozens of possible rupture scenarios in the time it once took to model just one, building a far richer picture of exactly where the greatest dangers lie before the ground ever starts to shake. Alongside it, a new generation of neural network models is already quietly changing how fast warnings can reach the public. Trained on earthquake sequences recorded across both Japan and California, these systems can now reliably identify an earthquake's location and magnitude within roughly 4 seconds of the very first seismic waves arriving at a monitoring station. 4 seconds is not prediction, and scientists are careful to draw that distinction clearly. It cannot tell anyone an earthquake is coming before it starts. But 4 seconds, delivered instantly to phones, transit systems, hospitals, and schools, can be the difference between a train that stops safely and one that derails, between a surgeon who has a moment to step back from an operating table and one who does not, between a child who ducks under a desk and one who is still walking toward a window when the shaking begins. What sets the Cajon Pass discovery apart from these other simmering risks is not just its scale, but its timing. It arrives at a moment when computational seismology has finally caught up enough to translate a discovery like this into something more than an academic finding buried in a journal few members of the public will ever read. The same 1,000-fold speed-up in simulation capability that researchers unveiled earlier this year means that emergency planners can now, for the first time, actually run detailed models of a combined San Andreas and San Jacinto rupture scenario, mapping exactly which neighborhoods, which water lines, which hospitals would face the greatest danger under this newly confirmed connected fault scenario. That capability simply did not exist even 5 years ago. Today, it means the gap between discovering a threat and actually preparing for it has never been shorter, even as the threat itself has just been revealed to be larger than previously understood. None of this changes the fundamental, uncomfortable truth sitting underneath every headline about California's earthquake risk. The state's official long-term forecast, a rigorously peer-reviewed model known as the Uniform California Earthquake Rupture Forecast, estimates that a magnitude 7 earthquake, still a genuinely serious and damaging event, should be expected to strike somewhere in the state roughly once every 6 years. Earthquakes of magnitude 8 or larger, the kind capable of producing sustained, catastrophic destruction across an entire region, remain far rarer, requiring an extraordinarily long buildup of unreleased strain that may only occur once every several centuries along any single stretch of fault. But rare is not the same as impossible. And the entire point of the Cajun Pass discovery is that the old assumptions about how these faults behave in isolation from each other may no longer hold. Older Californians do not need a study to remember what a major quake feels like. The 1994 Northridge earthquake, a magnitude 6. 7 event on a fault nobody had even mapped until it ruptured, killed dozens, injured thousands, and caused tens of billions of dollars in damage in under 20 seconds of shaking, collapsing freeway overpasses that engineers had assumed were built to withstand exactly this kind of event. 5 years earlier, the Loma Prieta earthquake near San Francisco, a magnitude 6. 9 rupture on a segment of the San Andreas system itself, killed dozens more and sent a section of the Bay Bridge crashing down in front of a television audience watching a World Series game. Both of those earthquakes were smaller in raw magnitude than the scenarios researchers are now describing. Both were single fault events contained to a single rupture zone, and both still reshaped building codes, emergency planning, and public consciousness for a generation afterward. A connected multi-fault rupture of the kind that Cajun Pass findings now suggest is possible would not simply repeat that damage at a larger scale. It would introduce failure modes those earlier disasters never tested, longer shaking duration, a wider radius of severe damage, and infrastructure failures spread across 2 separate fault corridors instead of 1. That history is precisely why seismologists resist the temptation to treat any single new study as a countdown clock, even one as significant as the Cajun Pass discovery. Science has been wrong about earthquake timing before, and it has learned, through hard experience, to be honest about the limits of its own predictive power. What has changed is not the ability to say when. It is the ability to say, with far greater confidence than a decade ago, exactly what shape the worst-case scenario is likely to take if and when the ground finally does give way. That distinction between prediction and preparation is not just a scientific technicality. It is the difference between a region that reacts to disaster after it strikes and one that has already modeled its way through the disaster before the first tremor is ever felt. Consider for a moment what a connected San Andreas and San Jacinto rupture would actually mean for the people living directly above it. Southern California is home to some of the densest, most heavily built urban infrastructure in North America, a sprawling tangle of freeways, high-rise towers, aging water systems, and underground utility lines that were, in many cases, engineered decades before scientists fully understood how these fault systems interact. Emergency planning documents across the region have long modeled single-fault scenarios, treating the San Andreas and San Jacinto as separate threats requiring separate responses. A combined cascading rupture does not fit neatly into either plan. It forces emergency responders, hospitals, and utility crews to confront a scenario that is larger in scope and less predictable in shape than almost anything currently built into official disaster planning. The economic exposure alone is difficult to overstate. Southern California anchors one of the largest regional economies on the planet, home to global shipping ports, sprawling entertainment and technology industries, and a population in the tens of millions. A major rupture along a connected fault system would not just damage buildings. It would sever transportation corridors that the entire western United States depends on for goods movement, disrupt financial and technology operations with global reach, and displace an enormous population from housing stock that, in many neighborhoods, predates the modern seismic building codes now considered standard. Recovery, by every serious estimate, would not be measured in weeks or months. It would be measured in years, and in some hard-hit areas, potentially in decades. And yet, for all of this, the most unsettling part of the story may be the one thing science still cannot offer. There is no clock counting down to a specific date. There is no confirmed trigger point that says, with certainty, when the strain building beneath Cajun Pass will finally release. Stephen Burns' 6 to 12-month window remains, by his own account, a pattern-based warning rather than a scientific forecast, and mainstream seismologists continue to caution against treating it as one. The peer-reviewed research is, in some ways, both more restrained and more disturbing. It does not claim to know when. It simply confirms that the mechanism for a worse-than-expected disaster, 2 major fault systems capable of rupturing together instead of separately, is real, mapped, and sitting directly beneath one of the most populated regions in the country. Scientists studying the fault continue to stress that this new understanding is not cause for panic, but cause for preparation, the kind of unglamorous, unhurried preparation that rarely makes headlines until it is suddenly, urgently needed. Retrofitted buildings, reinforced water infrastructure, faster simulation tools feeding better emergency plans, earthquake early warning systems reaching more phones, more schools, more hospitals with each passing year. None of it stops the fault from moving. All of it changes what happens in the seconds, minutes, and years after it finally does. For now, the pressure beneath Cajun Pass continues to build in silence, exactly as it has for centuries, indifferent to headlines, forecasts, and live stream warnings alike. The rock does not know that scientists have finally mapped the gate connecting 2 of its most dangerous fault systems. It does not know that 1,000 years of trench data have confirmed what researchers long suspected, but could never fully prove. It simply keeps grinding, fraction of an inch by fraction of an inch, toward a moment that no model, no matter how fast or how detailed, can yet tell anyone the date of. Somewhere beneath the streets of a city that never stops moving, the ground is the only thing standing still, and even that, scientists now warn, may not be true for very much longer.